Hey there, Calc folks, back here with another lecture in our series here on the application of integration. But in this lecture, we are going to go back and, like I had promised, I think in previous lectures, is look a little bit at the proofs of some of these formulas that we're seeing develop here in this chapter on the application of integration, and look at where these formulas are developing from, and how they relate back to the integration process, and how the integration process is going about proving these formulas as the formulas for these calculations. And we're going to look at the case for what is a distance, area between two curves, general slicing method, and the shell method. Disk and washer method are special cases of this, so we're going to just look at general slicing method, which then specified to those specific cases of disks or washers. That's where your disk and washer methods come from. So we're not actually going to prove disk and washer, but general slicing, and then shell method. Shell method is not general slicing method. It does involve slicing, but not quite as we anticipate. And the shapes we form aren't slices of a solid. They are these things called shells or rings. So keep that all in mind. And that is where we're going to head, folks. Here we are going to look at the case for, like I said, these integration proofs. And where all these proofs come from is our fundamental understanding of integration. If I flip over here to the notes, where all these ideas do come from is our fundamental understanding of integration. Now, what is going on here? Let me get this up. There we go. Using a new program here, folks, to kind of a little Stream Deck situation called Touch Portal to kind of run my program here, flipping my scenes. And it's still a little buggy. Actually, when it pulls up a window, if it minimizes and pulls it up, it sometimes brings up my background. It's a little laggy there, but here we are. Let's look at these integration proofs. The application of integration seen in our exploration of this topic, right? The applications of integration seen in our exploration of this topic all involve a definite integral calculation, and all develop from our fundamental understanding of the definite integral calculation, folks. That definite integral calculation that we perform comes from the understanding that what we are actually calculating is the limit of a Riemann sum. We are applying a limit operator to a Riemann sum, and we are forming what we call a definite integral operation, right? Or performing a definite integral calculation. When we take a limit and we apply it to a Riemann sum, we end up forming what we call definite integral calculation. And this developed back in the end of Calc 1 when we were introduced to the process of integration, when we were looking at the case of net area, right? Or you may have had it presented to you as physical area, right? But if we take a look here, right, and we do a little recall on net area, this is the idea we want to recall that when we calculated net area back in the end of Calc 1, right, in our introduction to integration, that net area was calculated using the definite integral calculation, but it was itself a limit applied to this. Let me see if I can highlight it all here. Applied to this Riemann sum calculation here. This Riemann sum calculation where we were summing up, in a sense, the area found in these rectangles that were defining this net area of space. And those rectangles, their area had a height determined by f at some observed value of x in the case subinterval from a to b. And delta x was the width of these subintervals. Right? This was where we were using n subintervals of our closed interval from a to b to divide up this net area of space. Delta x was the width given by b minus a divided by n, and x sub k was just simply a value of x in that k subinterval. Multiplying f of at x sub k times delta x gives us the area of each of the rectangles in these n subintervals of space, Summing those up gives us an approximate of the total, and applying a limit to that calculation as n heads to infinity will give us the true net area calculation. And we've seen that that limit can be connected to definite integration through what is known as the fundamental theorem of calculus, which we see down below here. I do think I got another quick recall. Yeah. This net area calculation for y equals f of x over the values of x in this closed interval from a to b is found by subdividing the net area space trapped between the curve and the x-axis over this interval of x into vertical regions forming along the x-axis, where for each region the shape is approximately the shape of a rectangle, where the area of this rectangle can be given by the geometrical calculation we have been aware of for years, and that is area is equal to height times base. If we have a constant height and a constant base measurement, if we know the height of the rectangle is constant and the base measurement is constant, the area calculation is simply height times base. Where in our particular case here, in the net area calculation, the base measurement was actually the value given by delta x. The width of each of these subintervals along the x-axis described the base of these rectangles, whereas the height of these rectangles was determined by the function we were integrating, right, at some representative x value in our kth subinterval. And that area was calculated by simply f at x sub k times delta x. All right. In terms of the area found in each of those, in terms of our area of these regions, they are then approximated. I think this is what's throwing me here, is we should maybe say approximated. All right. We'll say here net area for the, let's actually go this way. Let's call this A sub k, right? Which is an approximation for the area in the kth subregion. And then let's just make note that net area is actually the summation from k equals 1 to n for A sub k, right? Which we then approximate using the summation from k equals 1 to n for f of x sub k times delta x. And this becomes our way of approximating the net area in our case. Now, I do think I'll give you an illustration of this just to help you make some connections. Consider the net area trapped between the curve f of x equal to 2 plus 1/10 x squared over values of x in the closed interval from 0 to 1. In the closed interval from 1 to 4. Right? Here is our curve y equals f of x. That is this red graph that I have illustrated here. Right? And we are looking at approximating the net area trapped between it and the x-axis over values of x from 1 to 5. And you can actually see that net area is somewhat shaded, but it's hidden behind these bars, right? If we were to remove the bars, we would see that area of interest. But what we're using are these bars, these blue bars in this graph, to approximate this net area. Right? We have taken this closed interval from 1 to 4. Actually, I see I'm doing it from 1 to 5. Let me fix that. This interval from 1 to 5, and subdividing it into 4 subregions. So that would be 5 minus 1 divided by 4. 4 divided by 4 would give us a delta x equal to 1. That is the width of each of these subregions along the x-axis, or each 1 unit in length. And then what we notice I have highlighted here with the point on the graph that's kind of in this pinkish magenta color, that is the height of our function at some representative value of x sub k in that k subinterval. That's actually at the midpoint in those subintervals. So that's at 1.5, 2.5, 3.5, and 4.5, respectively. All right? And what we are highlighting here is the height of those regions, those subregions of this net area, can be approximated by looking at the function at those locations. All right? That is what we have highlighted above here. Right? If I want to approximate the net area in my graph, I can sum up the area found in each of these rectangles. What is the area found in each of these rectangles? Well, they have a base measurement, right? They have a base measurement described by delta x, the width of each of these 4 subintervals along my x-axis. Well, the width of each of those is 1, right? So that would represent delta x in that calculation. F of x sub k would be the height of the rectangular region, right? It's taking the place here of the height, right? And we're just using the midpoints in each of these subregions to indicate where the height would be occurring at on our function, right? And we see those 4 midpoints here. And that's describing the height of each of these rectangles. And if we add up all of the heights times the base measurements for each of these n equal to 4 rectangles, right, we are going to obtain an approximate of that net area that we would see in this illustration. All right, and we take note, we could make this approximation more exact if we consider more subregions. Now, in this case, I do lay out here. I note in this case that net area is going to be approximated by this summation here, where again delta x is equal to 1, and the midpoint of each subinterval is used. So x sub k, the value we're plugging in to our function f at x sub k, would be the quantity k plus 1/2, incrementing up by 1 each time we run through the summation. So what you can see, if you plug in 1, you get 3/2. You plug in 2, you get 2.5. You plug in 3, you get 3.5. You plug in 4, you get 4.5. Describing these midpoints along my x-axis in each of those subintervals. Now, this approximation grows more precise as we increase the number of subintervals. If we consider using 10 subintervals, this is what we would see illustrated. Right? Delta x would be 5 minus 1 or 4 divided by 10, or would have a width of 2/5. Right? Each of those subintervals is 2/5 in width. Right? And we are using, again, the midpoint here, right, which has to be found using the, again, midpoint calculation here. And if we set up the net area calculation in this case, it's going to become a bit more exact. In this case, that net area would just be the summation from k equals 1 to 10 for f of x sub k times delta x. Where, again, in this case, delta x would be 2/5, and the midpoint would be given by a plus k minus 1/2 times 2/5 in value. Quantity times 2/5 in value, which would give you a k value of 2/5 k plus 4/5. So as you plug in k from 1 to 10 into that, it's going to tell you all the midpoints for each of those subintervals along that region seen here. All right? Take note. Remember, this is all recall. This is, again, setting up how we go about this calculation for net area. And we're going to rely on all of this, these ideas in our proofs, folks. These are all going to be the ideas we rely on in our proofs. All right? Remember, this net area was then made exact by applying a limit, right, as n, the number of subregions, approached infinity. Add more and more subregions, divide up that x-axis from a to b into more and more subintervals. You're going to get a finer approximation, a more precise approximation, an approximation that has greater precision. Right? And how do you get it to become exact? You look at its behavior overall for an arbitrary value of n as n heads off to infinity. Right? And we see that occurring here or recall that occurring in our calculations. Where from here then, once we apply the limit to the summation, we were able to, through the fundamental theorem of calculus, make a connection to that net area calculation and definite integration, which gives us the definite integral, the definition for the definite integral, where we recall, right, from the definition of the definite integral, net area, which is equal to the summation, right, is equivalent to the integral from a to b, the definite integral calculation from a to b for function f of x dx, where from the fundamental theorem of calculus part 1, we make connection back to this idea. And in part 2, we make connection to this idea seen here. Where do we evaluate this? we have to consider what is the value of big F related to little f, where how does big F relate to little f? Its first derivative is equal to f of x, or it is the antiderivative of little f. And to evaluate that antiderivative across these bounds from a to b means just to evaluate it at big F of b minus its value at big F at a. All right? That is what comes about from the second part to the fundamental theorem of calculus. But we make this connection to this idea of net area being this limit of this Riemann summation to definite integration through the definite, or the first part, which is lays out also the definite integral definition, and then through the second part, right, brings up this calculation method using the antiderivative and the relationship there. Right? Now this is the idea that we are going to use in all of our proofs. Now, and the way we're going to do that is by changing our understanding of f of x sub k in the above understanding. Right? Function f of x, or function f of x sub k in this Riemann sum calculation doesn't just have to be a scalar value function f, right, where we are interested in the net area trapped between that function f and the x-axis. That function f can assume different forms, right? Can assume different forms, or a different understanding, or a different interpretation, we might say. Where just replacing it in this understanding for net area may certainly take away our connections to net area and give us something else to connect to. Distance, area between two curves, general slicing rule, shell method, right? Replace the question mark with those calculations, right? By simply rethinking how function f of x is being presented here in this Riemann sum calculation. All right? That is the technique we're going to consider here in our proofs, and I make note of that here in this note. Right? This occurs in the following proofs of the integration formula accounted in our study of the integration process. We're going to look at interpreting f of x sub k differently, right? And making a connection back to it. Let's start with distance formula. And consider proving that when we calculate distance, right, along a linear path over time t in the interval from a to b, given the description of the velocity vector v bar or via t, no vector there, via t, that it is just the integral from a to b for the magnitude of via t dt. Let's consider proving this formula. And the way we begin this is a lot like we begin the net area calculation. We take this interval of time from a to b and we subdivide it. We subdivide it into n subintervals of time. For instance, it might represent 5 seconds of time, and we divide it up into 1 second intervals, right? We divide it into 5 equal portions, or maybe it represents 10 seconds of time, and we divide it into 20 portions, each 1/2 second in length, right? This proof begins by subdividing our interval of time into a set number of subintervals, n subintervals, right? Where we now let delta t be the length of the case subinterval. And again, what I'm missing here is I might say delta t is equal to, again, b minus a divided by n, as it was similarly in the case for delta x, right? And it's going to be this, right, length of the case subinterval of time. And we let t sub k, a lot like x sub k, be a value of time found in this case subinterval. Right? We might have that time interval from 0 to 5 seconds, right? Divided up into 5 subintervals, and maybe we pick the midpoint of time in each of those. 1/2, 3/2, 5/2, 7/2, right? 9/2. All right? T sub k would just represent those values. Now remember, T sub k can actually be any value in those subintervals. We pick some consistent ones to sometimes aid in our calculation, but in theory that x sub k can be actually any value of x in those k, or in the kth subinterval for the n subintervals. right? So the proof begins by starting there. And then goes about noting, well, the exact distance traveled over the k subinterval of time, right? If we just look at a kth subinterval, if we just look at one of those smaller subintervals of time, and consider approximating the distance traveled over that k subinterval, we're going to rely on our understanding of distance, time, and speed, right? We go back to a rather fundamental concept of how distance relates to time and speed, and we know from traveling at a constant speed for a set amount of time that distance is always just speed times time, right? If we travel at 60 miles per hour for 3 hours, what? We have traveled 180 miles, right? If we travel at a speed of 60 miles per hour for a time length of 3 hours, we know the distance we have traveled is 180 miles in those 3 hours, right? So if we think about this kth subinterval of time, where delta t is the length of time traveled over this k subinterval, right? It's going to be this measurement of time in this calculation. And keep in mind that in terms of motion in space, the magnitude of the velocity, or the absolute value of the velocity at time t, represents speed. Here we're going to look at time t sub k in our kth subinterval, right? If we take this speed measurement and multiply it by this time measurement, we will get an approximate for the distance traveled over this kth subinterval of time. And that distance traveled over that k subinterval right, can be approximated as d sub k. We might say d standing for distance, sub k for the distance over the k subinterval of time, and it would just be approximately the speed, right, times the time traveled. Right. Now, with being able to approximate the distance traveled over each of these k subintervals of time, right, we can calculate an approximation for the total distance traveled by summing up the approximations found in each of these k subintervals. And you might start to see this connection back to our calculation for net area seen above here. Folks, this, there's not much difference here. What is truly different is this quantity coming about right here and the variable that we're considering integrating with. All right? Start to take note. This looks a lot like the net area that we had seen previous. Right? So total distance, right? When we think about total distance, it can then be thought of as this summation from k equals 1 to n for d sub k. Right? D sub k, right? D sub k again being the distance traveled on each of the k subintervals all summed, where we can approximate that by summing over each of our approximations for d sub k. All right? And then how do we make that exact? If you take note of what we did above, we apply a limit. All right? To make this approximation exact, we apply a limit as n heads to infinity to that approximation. And the distance traveled then is equal to the limit as n heads to infinity for this approximate calculation. And again, all of this should look very familiar to what you see above. All right? Where once I have this exact calculation of distance using this limit of the Riemann sum, we can go back and take a peek at the definition of the definite integral, where in that definition, simply letting delta x be equal to delta t, replacing x with t as the independent variable, and letting f of x sub k be represented by this function given by the absolute value of v at t sub k, we can conclude that the limit of this Riemann summation we have set up above, right, is just equal to this definite integral calculation, where we are replacing the delta t and the dx, the comparable dx in that definite integral definition with delta t and dt, and we are replacing the f of x sub k and the f of x seen in that definition simply with this function, the absolute value of v at t sub k and the absolute value v at t. All right. That is what's happening there, is we're just going back to that definition and substituting in these values and drawing this conclusion. Right? We are just going back to this idea here, replacing this quantity with the absolute value at v t sub k and replacing this quantity with delta t, which means over here in this argument, I can replace the f of x with the absolute value at v sub t, or v at t, and replace the dx with dt. And this calculation just becomes another fundamental definite integral calculation approached as we had seen here on the right-hand side. Now with the absolute value function, you do have to watch the graph. When you dip below, you do have to compensate for the negatives by maybe approaching the calculation piecewise. But the connection can be made here back to the definite integral that links this limit of the Riemann sum in this proof to the definite integration process, to the final formula that we have. All right? And all this setup that we see develop here for just taking note of how we calculate distance, approximating it over the k subinterval of time, approximating it over the entire interval of time, and then making it exact with the use of a limit is the process of integration, folks. It is the essence behind the application of integration. What are we stuttering this chapter? Stuttering. I know I'm stuttering. Isn't that there I go, Freudian, right? It is a study of, right? It is a study of the application of integration. And so far we've been studying the application of integration just in different real-world examples. Right? Different geometrical examples. Right? But it's also looking at the study of the application of integration in the context of these proofs. Being able to understand the integration process that's behind each of these formulas that we present in this chapter. Right? And making the connection to those formulas and this process where they come about from. Right, these proofs. So yes, I do not want to overlook the proofs in this chapter, folks, and just focus on the formulas, because it's not the 8 or 9 formulas that are presented in this chapter that are important, right? They are only part of what's important here, folks. They aren't all of what's important. The other aspect that's important is understanding where they come from, because that is also technically the application of integration. Right? So there's kind of this double meaning to the chapter title, application of integration, folks. It's real-world examples where we see it applied, but it's the application of the process to develop these real-world applications. And again, my hope is that through understanding where they develop from, is these aren't the only 8 or 9 formulas where integration is applied. The world likely, in our reality, likely has an infinite number of applications. Think about it. There's new undiscovered areas where these ideas can be applied, folks. So, understanding how these ideas apply themselves might make you one of those individuals who discover some of those new areas. All right? Just throwing that out there, folks. Give you a little inspiration, right? A little motivation. So we do make that connection down below here to that net area calculation, right? With these simple replacements, we can make this into this calculation that we see in our proof, or in our formula that was presented, right? Let's look at, notice I do make the connection here, right? Note in the proof above, everything I just said kind of is also summarized by this note. For the sake of brevity, we're a half hour in. You can see we've got a few pages to get through here. We got 2 more proofs to look at. Yeah, I think we're all right. No, 3 more proofs. Area between the curves. This one we can probably relate to a little better. I did show you a little quick way to understand this by simply thinking of this as an integration process that distributes itself across the difference, and then you are finding one net area minus another. which is going to leave you physical area trapped between two curves. Right, and that is what we are looking at here with area. That's not net area trapped between two curves. It is physical area trapped between two curves. And it does also, though, follow rather readily from our understanding of net area. Right? It also begins by subdividing that interval along the x-axis from A to B into n subintervals, where we let delta x be the width of the k subinterval, and we let x sub k be a value of x in that k subinterval. Right? As for looking at the area of this kth region, right, we also noticed also rectangular in space, right? And I do think I have an illustration to give you down here, right? Go back to this illustration here. Here we have this function f of x. Here we have this function g of x. And when we subdivide this region, right, into its n subintervals, each of those subregions are also rectangular here in space. Their width, right, the base measurement of those rectangles, each measures delta x, as it did back in our understanding of net area. And the height is the difference between f of x and g of x. F of x minus g of x at each of these different values of x in these n subintervals at the value of x sub k in the kth subinterval. The difference between f and g is what gives us our height calculation. All right. As for the area of the kth region, it's also rectangular in shape and can be approximated using the formula for the area of a rectangle, area being equal to height times base. All right. The approximate area in the k subregion then is going to be this height measurement, the difference between function f at x sub k minus function g at x sub k. Realize that for each of these k subintervals, x sub k is highlighted at the magenta point given in our graph here. All right, so here's f of x sub k minus g at x sub k, and it's going to give me that distance, which is going to mark the height of that rectangle. And delta x, right, is going to be our base measurement. Right? How far is it across this base, the length of the base? Right? Or the length or the measurement of the base measurement. Right? So when we think about approximating the area in the k subregion, it is just f of x sub k minus g at x sub k times delta x. It is just this location on the y-axis minus this location on the y-axis as a group, a quantity, times the base measurement, right? This distance times this distance. And then we can find an approximate for the total area by summing that up for all these n subintervals. Right? We can sub from k equals 1 to n and come up with an approximation for that total area. All right? And to make that then exact, right? As for making this area exact, we just apply a limit as n heads to infinity, and we're applying a limit to this statement here, right? Limit to the summation, the Riemann summation that we formed above, where the Riemann summation is a slight variation of our case for net area, right? It really is a slight variation, right, for this case for net area. Instead of having just f of x sub k times delta x, it's f of x sub k minus g of x sub k times delta x. What we can do is replace our understanding back here in the definition of the definite integral for f of x sub k with another function that involves f of x sub k minus g of x sub k. Delta x is delta x, and then our integration will follow rather naturally. The value that represents f of x sub k is going to become our integrand as we see it over here in this definite integral calculation. All right? We're going to apply a limit to this idea. And then what we note is we are replacing f of x sub k from our definition of the definite integral with this quantity seen here. That is what we saw above for f of x sub k. Slight variation on f of x sub k. Where now in our definite integral calculation, that quantity f of x can be then replaced with the slight variation f of x minus g of x. Right? And this becomes our defined calculation for area trapped between two curves. Again, looking back through that process, folks, it's very similar to the net area calculation. Right? It is very similar to that case of the proof for net area, and also what we've seen now is the proof for distance traveled. All right, let's look at general slicing method. A little further along here. These move a little quicker. If we consider the general slicing method here we have this solid forming along the x-axis of space over values of x from a to b in 3 dimensions, where the cross sections perpendicular to the x-axis are all defined by a of x, all defined by some area function that's dependent upon its location along the x-axis. And if this is the setup, then the volume is calculated by integrating from a to b, the area function all integrated with respect to x. And like the other proofs, we begin by subdividing that closed interval from a to b into n subintervals, where delta x again is going to be the width of each subinterval, and x sub k is going to be a value of x in the k subinterval. But in terms of our solid, when we subdivide our x-axis this way, it subdivides our solid into n slices. Right? It slices up the solid along the x-axis, right? With each slice falling along the x-axis. Where the volume of each slice can be calculated using a familiar geometrical calculation for volume of a solid, right? Where we might note the following generic illustration for the case of n equal to 4 subintervals. All right? Here we have this illustration of a solid, right? This solid forming in 3-dimensional space. Here's its base down in the xy plane, right? Shadowed in the darker gray. And this solid is occurring over the x-axis from A to B. It does have this curvature to the top of it. All right? When we look from above, it's going to look like this base solidified down here in gray. And what we are doing is slicing it up into n subintervals on this interval from A to B. Here I've sliced it into 1, 2, 3, 4 subintervals in my illustration. And you can see how that region of space is being sliced with those cross sections. All right? Now, to approximate the entire volume in here, we can do what we've done before, is we can approximate the volume in each of these n slices. We can start to think about what is the volume found in the kth slice, right? Well, each of these slices is approximately what we might call the volume for a, let's be a little more specific here, rectangular prism, right? With cross sections parallel to the base, whose area is given by the constant value of A. All right? And it has a height perpendicular to the base described by H. Right? Each of these cross sections, or each of these slices, you can see here has a cross section, right, that might be used to approximate what we might say is the base of this rectangular prism. And the height, or what we might say is the length of this prism perpendicular to this base, right, would have a measurement described by H. And in this case, the volume for this prism would be described by simply volume equals A times H. Actually, we just need prism here. What we ought to note is, as for approximating the volume of each slice using the above geometrical formula, it is given by this calculation for a rectangular prism. And I do think we want to leave this as rectangular. it is going to be a rectangular prism that we always see happen here, folks. All right, and that rectangular prism is going to play a role. It's the fundamental theorem is, it's not. Back up. It's not always a rectangular prism. For a prism, disc and washer method, those aren't rectangular prisms. Those are circular prisms, cylinders, right? Or in the case of a washer, a cylinder minus an interior cylinder, right? So, yeah, let's make that sure that's prism, but the volume for this prism is described by the volume is described by this formula here. And by the calculation for a rectangular prism, right? This illustration, it just happens to be, in this generic case, a rectangular prism. But it doesn't always have to be. Depends upon the area of the shape for those cross sections. My areas of my cross sections are all rectangular in shape here in my illustration. That's why I'm going to think of them as a rectangular prism. The area of your cross sections, well, depending on the solid, might change. Disc method, they're cylinders, cylindrical or circular prisms, which are cylinders, or washers, which are basically cylinders minus cylinders, right? A cylinder with an interior cylinder subtracted from the interior, right? So let's make sure we're clear on that, right? And if we set that up in this case, we just note that we are going to note the area here. The area is part of the setup. If we take note of it at each possible value of x at each x sub k value in all our n subintervals, right? We're going to get an approximate area of the base measurement. And then if we times that by the actual width of that slice, right? Delta x, that's going to give us, in a sense, a height measurement. When we think of these prisms in my illustration, because the x-axis flows horizontally, the prisms are actually aligning themselves horizontally along that x-axis, where they're actually forming kind of, their base is standing up on its end, perpendicular to the x-axis, and their height is forming along that slice. All right, so their height becomes more of a length, and their base measurement is described by the area of the cross-section, right? Their height measurement is more of this length, and the area of this cross-section becomes more of a description of the area of their base. All right? Now, I do have a good illustration of this down below. As for approximating the volume of the entire region, then you can sum all those up. All right, actually, here it is. Yeah, here's my illustration I was trying to explain above. Right? We're just looking at the kth slice. I'm really the second one in my illustration. But it's this cross-section whose area we know, because that's part of the setup, at x sub k. X sub k is this observed value of x in the kth subinterval. This k subinterval being this distance here, traveled by this indicator given by delta x, this green indicator indicating that length of that kth subinterval along our x-axis. Right? That length becomes the length of this prism. The A at x sub k becomes the area of its base, and the area of the base times this length will give me the volume of that rectangular prism. And the volume of that rectangular prism will approximate the volume of space in that kth subregion of our solid. Now, to find total, you just add them all up. All right, and to make that exact, right, here's an illustration of what they would all four look like for each of the four slices of this solid, right? There was the one I had just highlighted, the second one in, but the first one might look like that for that very first cross section. The second might look like that for its cross section. The third for this, the fourth for this, right? Where what we are using for the area of the base is the first 1, 2, 3, 4 cross sections seen here. The fifth and final cross section isn't used. It's the end of the region, right? If we had gone beyond this another bit, we could use that cross-section to approximate another slice that might be considered. Right? But it's these first four cross-sections that have being used as area of bases down here in this illustration. 1, 2, 3, and 4. This fifth one, not so much. Right? If we then take their lengths along the x-axis, delta x, we can think about describing these rectangular prisms that form in each of those slices. And adding those up becomes an approximation of total volume. Now, if we start to subdivide that over smaller and smaller subregions and look at that behavior as n heads off to infinity, we then get a total exact volume calculation given by that limit. And we see that calculation seen here. All right. Where from the definition of the definite integral, we can go in and replace f of x sub k with this a of x sub k description. Delta x from this calculation is still just delta x. So what we had there given in the definition of the definite integral looked a lot like this, but instead of capital A, we had little function little f, which translates directly from the definition into this integral from a to b for the capital of a of x dx. We are just going back to our fundamental understanding in that area. Given by the definition of the definite integral, this understanding right here. And all that's happening is this is turning into function A, which implies that by definition that has to become function A. All right? That's applying the definition of the definite integral. It is then the fundamental theorem of calculus part 2 that allows you to go on to say this, right? Where this is going to become this, where this must be the antiderivative of this, implying this. Let me clean all that back up so I don't forget to change it. All right? But that's all we're doing is replacing function f with function a in that fundamental definition, that area description of those cross sections. Delta x is representing not the base measurement for the rectangle that we're using in that area, but delta x now is representing the width, or what we might call the height of the cross section if we were to tip it over onto its base. All right. So that is volume by slicing, folks. All right. That's where we get the volume by slicing formula. In the case of disk method, a of x is just replaced by the area of cross sections that are circles, right? And washer method just replaces the area of the cross sections a of x with the area calculation for concentric circles, one circle inside another. All right. Now, lastly, we have here shell method. Let me give you a little bit of shell method here. Where if I get this aligned, let's see here. Again, we should be familiar with the setup for the shell method, right? We are looking at what? Taking this region of space trapped between these two curves, f of x and g of x, on this interval of x from a to b, and in this situation, in the classical approach, revolving that around the y-axis. And as we revolve that entirely shaded region around the y-axis, it's going to form a solid of revolution, we understand, right? Where in this setup, known as the shell method, we can calculate it with this above formula. All right? And this formula does begin by subdividing. You can see here I've gone from a to b, and I have subdivided this region into n equal to 4 subintervals. In general, we divide it into n subintervals, right? Where again, delta x is going to be the width of each subinterval, and x sub k is going to be a value of x in each of these k subintervals. All right? This in turn is going to subdivide this region. You can see here this region has been subdivided into 4 subintervals here in this case. I went with n equal to 4 just to be able to illustrate. It has a width from here to here, from the left side of the region to the right side of the subregion. It has a width given by delta x, right? Where you find that taking b minus a divided by n as we always have. All right? But when we go to revolve the subregion now, right, here around the y-axis, it is going to form, right, where when each of these subregions is revolved about the y-axis, the result is a shape approximated by the shape of what is called a shell or ring. And you can see here in my illustration, I have illustrated a shell or a ring for you folks. Right? Here we have this shell or ring. Right? Here I have my wedding ring, folks. I don't always wear it while I'm working on the computer. I always set it off to the side. But that's what we're talking about. A ring. Right? A ring is approximately that. If I spin this profile of my ring around this y-axis, it will form a solid of revolution. Right? And that solid of revolution could be calculated if I had the description of my ring's profile in the context of f and x and g of x. I could describe the volume of that. Right? So this is what we're going to form when we revolve one of these subregions, where that's the volume we're going to want to focus in on, is how do I think about setting up the calculation for the volume of this subregion, right? And what we do take note is x sub k, right, is going to be a value of x, right, that's occurring in the kth subinterval here along my x-axis, right? That is actually marking what we call the kth ring of this revolution. Nope. Right? Note, the volume of a shell or a ring, if we just think about the shape in general, right, has a radius, where in this case we might note that radius could be summarized from the distance from here to x sub k. On average, it's going to have a radius given by x sub k, right? And a width of w, right? The width from the left to the right of that ring is given by w, and has a height, right, that we might just call h in value. And if we had a ring with a radius of r, right, a width of w, and now that radius is really, I should say here, with n. I should be careful there. Let's be a little more specific. Average radius of r, right? You notice it doesn't have the same radius over that distance from the origin, but it might have an average radius that we call x sub k. The innermost radius averaged with the outermost radius would point you right to the middle, right? And that's true for every single observation of x in there. The average would be at x sub k. All right? So with an average radius of r, a width of w, and a height of h, the volume of the shell or ring can be approximated as follows. It is going to be 2 pi r times h times w. Now, where that comes from is the idea that if you were to slice this ring, if we sliced here in the xy plane, this ring vertically down the y-axis along the xy plane, it would slice this ring into a shape where if you unfolded it, right? If you unfolded it, let me see if I can illustrate here with just a little piece of paper. Right? Let me see if I can make a short little model, right, for my ring. Here's where our formula is coming from. Here is my ring shape, right? You can certainly see that in our illustration there, right? Made with just a little piece of, well, a little sticky note, right? Folded up a couple times, ringed up. Right, it could certainly fit on my finger as a ring, right? That has a height to it, right? It has a height to it. It has a average radius. Now, certainly it's thin enough, you might say that average radius, you could measure it one place and use it to approximate the entire radius. That is kind of the idea of going off to infinity, right? But if we wanted to break out our calipers and measure this radius from the center down to both the inside and the outside of this ring to a very minute scale, we could average that radius and come up with a measurement of r. And it has a width. There's a tiny microscopic width, and not really microscopic. Certainly you could measure it if you had a fine enough instrument to the width or the thickness of this ring, right? Just like the ring on my finger, right? There's a tiny microscopic thickness to that. Not really micro, but yeah, you could measure it. It's certainly there, folks. You can see that thickness, right? That would be the width, however thick it is from the outside wall to the inside wall, right? And where this formula is coming from is certainly, well, let's look here. It is just the volume for a rectangular solid. If I was to take my shape, my ring, slice it, and unfold it, what I have here is a rectangular solid where the height is certainly observable. The width is what we see on that microscopic scale, right? Measured this direction, that tiny scale with my ring of paper here, with my tiny shell. And its length, this long measurement around here, if you think about where that came from what is essentially the circumference of the ring, the average circumference of the ring. All right? This length, if we thought about this as a two-dimensional ring, right, that didn't have any width, it would be the circumference of this edge. But we're really thinking of it as more of an average there. So it would be the average circumference around here. Well, how do you find the average circumference around there? You take 2 pi times r, the average radius measurements. Right? This is what's giving me the average circumference. Remember, circumference, if you know the radius, is just 2 pi times the radius. All right? So here it's just 2 pi r. Right? 2 pi r is the circumference, is the length of this rectangle, or this rectangular prism. Right? This is the height measurement, and then this is the width. So what do we know? Finding volume. Length times width times height will give us volume. And that's the 3-parameter formula we have here. Right? Now, in our setup, if we go to set this up, the radius, right, that average radius, the radius of the, we might say here, kth, let's be a little more specific. Trying to turn off the notation there. Of the kth shell or ring would be approximated by x sub k, right? That would be approximated by the value of x sub k in that kth subinterval that is forming this ring along our x-axis. The width would be given by delta x, right? That's the width of this kth subinterval, right? And as for the height, it would be the distance between the lower and the upper bound here, right? It'd be the difference between the lower and the upper bound at some representative value in the kth subinterval. Again, we could even go back to thinking of this illustration back here. What if I took this region and revolved it around the y-axis? What would be the volume for that solid? Each of these rectangles, when revolved around the y-axis, would form one of those shells or rings that I see down below there, right? The x sub k value would be the radius of that shell or ring. Would be the average radius of that shell or ring. The width of that shell or ring would be delta x, and then the height would be this distance. Well, that distance we know is f of x sub k minus g of x sub k. That's why these two formulas look so familiar, is that distance is being used the exact same way in this calculation. Right? So if we plug in those values, r becoming x sub k, that average radius, that height being f of x sub k minus g of x sub k, and that width being delta x, right? This would become an, let's be careful here, that would be an approximate for the volume seen in the kth subregion. It's not the exact. That would become an approximate, And for the total, right, the total would be found here by summing up the values found in each of the kth subregions from k equals 1 to n. That would give us the approximate volume, which we would understand as this calculation here on the left. Right? This approximate then could be made exact by applying a limit, where from the definition of the definite integral, we can connect this limit calculation over to the integration or the definite integral calculation we see here. All right? The f of x sub k that we understand back in our net area setup is this value 2 pi x sub k times the quantity f of x sub k minus g of x sub k. It is a complex function built with the difference of two other functions multiplied by this quantity 2 pi times x sub k, the independent variable, right, in our problem, the observed value of x in this case subinterval. Right? But if you just take that understanding for this and replace it with this, that would be replaced with this in our understanding. And F4, let's go ahead and highlight that product. That would be multiplied by delta x back in that definition. And when we translate this over to a definite integral, it does become just an integral from a to b with respect to x, where your integrand would come from this quantity, 2 pi x sub k times f of x sub k minus g of x sub k, where in the definite integral, we basically see that quantity become the integrand, but we ditch the k on the x. We ditch the sub k, right? We don't have k subintervals anymore. Remember, the theory says that when we integrate, we're really adding up an infinite number of items here, right? At each and every x value from a to b, we're calculating this integrand value. Where if you think about that integrand's value, all right, go back to our ring here, that integrand's value, that 2 pi x, that 2 pi x is just the length measurement, right? It is just that length measurement. Whereas the f of x f of x minus g of x is just this height measurement, right? And we're integrating that across all of these little widths, where when we approach infinity in our limit, they all become infinitesimally small, or really just become lines in our space. Right? So in terms of shells comprising this region, we have these little two-dimensional rings that end up comprising up that whole solid. Right? For every single layer, we have this, and I could kind of illustrate that by curling this up even smaller and saying, if we thought of this as being infinitesimally thin, right, we could see all those infinitesimal layers, right, thin layers would be formed, right? And we're calculating each and every area of each and every one of those layers. And then we are adding up those over all the infinite values of x we have from a to b, right, in our calculation here. This is the integration process, folks. Up to this point, I've kind of been approaching it with that understanding of it's this infinite summation and kind of interpreting that integral in that way, right? And I wave my hand over that like it's magic, right? It's not magic, right? It's this integration process where you really are interpreting in the calculation of a definite integral a limit of a Riemann summation, where you were introduced to limits of Riemann summations back here in net area. All right, back here in your understanding of net area, where in this understanding of net area, you are just replacing the function in your understanding of the limit of the Riemann summation with some other function that you've prepared in a similar manner, right? That you've prepared using the methodology of a Riemann summation, right? Which is what we learned in chapter 5, which defines net area. And then all a Riemann summation, and then, summing that Riemann summation with a limit applied to it, and leaving your upper bound undefined in terms of the number of subintervals and letting them approach infinity, you can look at the behavior of that calculation, right? And you can actually see the exact net area value. Well, that function f of x can switch up, and that integration there, it can be interpreted other ways. So this Integration still applies to that f of x, but it doesn't necessarily mean net area. And what we saw was this understanding of either distance in that case, where f of x became the magnitude or the absolute value of the velocity function at time, or it became the area between two curves, f of x sub k minus g of x sub k, or the f of x minus g of x, or it became the shell method, a of x, or in this case of, that's disc and washer method, slicing rule. And in the case of shell method, it became the volume calculation for the shell, or the area calculation for those infinitesimally thin small shells, which was 2 pi x times f of x minus g of x. All right, folks. That is some of what we want to take away from this section in this chapter also. That is some of kind of the implicit understanding that you want to kind of also key into in this section when it comes to what it means to be the application of integration. We just saw the integration process applied to develop each and every one of these formulas seen in our proofs. All right, so that is also something you want to develop in this chapter. All right, is a bit of an understanding of where these formulas come from. As I said, this process isn't just applied in these 8 or 9 formulas we're going to see presented in this section on the application of integration. Right? In theory, you could say that there's an infinite number of situations where you could apply integration in this manner. Right? And if there's an infinite number, certainly they haven't all been discovered yet. So understanding this process, there's a lot of ways that there's hope out there, folks, for that there might be something that you might be able to discover where the integration process could be applied. So, I always like to throw that in there in this discussion, right, on the integration process. And I always like to make sure that I show you these proofs, because this is some of the essence of the chapter, folks. These proofs can't go unchecked, right? So you can see here they are a rather long lecture if I was actually to page through all this with you. Right? It is something like 12, 13 pages. Right. Notes. It does include some illustration, and the equations do take up a little bit of space, and I have increased the font size to make it a little easier to see here. But this is a rather long lecture. So you may want to break this down into parts. Right? But the time you're watching this, I shouldn't even say that. So, but with that said, I will go ahead and close this down. We are at 1 hour and 7. Probably the longest one you're going to see this semester. But you made it. So we will see some more proofs. They most likely will now incorporate themselves into our work, folks, or actually into my future lectures. And we'll be able to approach those proofs maybe a little quicker, right, now that we've had this formal lesson where we walk through the proof for 4 different extra cases along with net area. Right, and made those connections in those 5 areas. All righty, folks. I hope you're hanging in there. Let me come over to this. I hope you're hanging in there. It's been a long semester. It's going to be it's been a long week. It's a long lecture. It might be a long semester for some of you, but let's hope it's good. And I hope you're all right. So, see you in class, and we'll go over all this then. See you next time.